Okay, so it might just be worth having a look at one or two spectra, and like that, have a look at the spectrum, have a look at the structure, and just see what we can see. So here we have propane, an active pharmaceutical ingredient, and here we have structures of propane. And this is showing us whether it has been protonated or deprotonated. So this is largely based on what solvent it's in. So the solvents here are either 0.1 molar sodium hydroxide, which is basic, and we have a 0.1 molar solution of hydrochloric acid, which is acidic. In an acid, we're going to have protonation, so that's the adding of that H plus ion or that proton, and in the NaOH, we're going to have deprotonation, which is the loss of that proton. Okay, and where we're seeing here is in two spots, both around those nitrogen. So we have an ammonium group here, so that's the NH3 plus, and we have that being deprotonated here to NH2, and you can see the lone pairs of electrons available. And then we can also see it on this amino group here, okay, so protonation and deprotonation. And we can see that it has quite a big impact on the spectrum. Okay, so we do see that beta chromic shift, and we also see that increase in intensity and absorbance. So when we have deprotonation in that basic solution of sodium hydroxide, we see that beta chromic shift, so our lambda max has moved up towards that red region, and we have a reduction of absorbance. With our hydrochloric acid, we have a lambda max at a lower value, okay, and we also have an increase in absorbance. Okay, so within propane itself, we have that benzene chromophore, and it's been extended. Okay, so we have lots more added onto it. So we have a C double bond O group. If we can go back and see where we can see that, a C double bond O. So we have that double bond, and we have those oxygens with lone pairs of electrons. Under the acidic conditions, we have that lambda max value of 279. When we have we also have a chromophore that has been extended, okay, so as in it has been immediately extended. Okay, so directly bound to that chromophore, we have that carboxylic acid, but what we also have now are these oxychromes. And the oxychromes are in the form of that amine group. When we're in acidic conditions, those amine groups are protonated, so they don't function as oxychromes then. Okay, so if we have a look, that is because those lone pairs of electrons are gone, okay, they're used up. It is only when it's being deprotonated that we're actually gaining access to those lone pairs of electrons, and those lone pairs of electrons can be excited from the ground state to a higher state, giving rise to this new peak. Okay, so just be mindful of that. So this is a recap from what I've just said. So under those basic conditions in that sodium hydroxide, that amine group is becoming deprotonated. We gain access to those lone pairs of electrons. They can interact with that chromophore to produce a beta chromic shift and a lambda max of 270. So just be aware, it's very, very important. And again, it is something we'll see with our methyl orange experiment next week, that we will have that the solvent that we use, the pH of the solvent, does have an effect on our lambda max, does have an effect on our absorbance intensity. And we can see that again here in phenylephrine. So again, we have our benzene chromophore, and we have a few oxychromes on here that can cause a change in our spectrum. So we have benzene, but we also have this oxygen group, okay, so deprotonated hydroxyl group here. And we have access to those lone pairs of electrons. We also have an amine group down here, okay, and depending on whether it's been protonated or deprotonated is going to affect this spectrum. So again, here we have our NaOH, a 0.1 molar solution of it, and we have a 0.1 molar solution of hydrochloric acid. So again, in an acid, it's being protonated. We're adding those protons. So that's this structure down here. And in NaOH, it's being deprotonated. So we're losing those protons. And that is up here. So how does that affect the spectrum? So again, we have our chromophore is not extended. Okay, so we're talking about that. We're talking about that benzene ring. But we do have oxychrome, okay, so we have that phenolic hydroxyl group. Okay, so when we have an OH directly bound to a benzene ring, we can call that a phenol group. And this can function as an oxychrome under both acidic and basic conditions, because no matter what way, even when it is protonated, we still have access to those lone pairs of electrons, all of which can be excited. Okay, so this hydroxyl group will always be oxychromic. So under acidic conditions, it's protonated and has 2 lone pairs of electrons. So we can see those here, 2 pairs. And when it's deprotonated, we have 3 pairs. Okay, we can, and these lone pairs can interact with the benzene ring. In its UV spectrum, we can see the betachromic and hyperchromic shift that occurs when 0.1 molar NaOH is used. So again, our betachromic, it means we're getting a shift to the red region, and we're also getting an increase in absorption, okay? So that is our hyperchromic shift, with using that language. Under acidic conditions, we have a lambda max of 273 nanometers, while under basic conditions, it's 292. Okay, so we can see that it does have a very real impact. And again, this is something that we will see in the lab next week. More calculations. So again, there's quite a few calculations in UV-vis spectrophotometry. And one of them is calculating the pKa, and that has to do with those carboxylic acid groups, and it basically is determining how acidic a group is, and based on the absorbance we can determine, and based on the pH being used, we can determine the pKa value. So this is obviously massively important when we are dealing with those groups that are pH dependent. So like in propane and like in phenylephrine. So the equation that's used, okay, and just be aware this is specifically for an acid at the moment, okay, so for a base, the log term is subtracted, so rather than having pH plus a log, it'll be pH minus log. We can determine the pK values. So let's just look at the acid for a moment, okay? So here we are working out our pKa, so this is known as the strength of our acid, is equal to the pH used plus the log of Ai is the absorbance of the fully ionized species minus the measured absorbance, and divided by the measured absorbance minus the unionized species. So we can look at an example of that. So what we have here is our example. So let's look at the question. And again, here it's very, very important for us to be able to identify information that is relevant and information that is not relevant. So this is all based on phenylephrine, which is the compound that we just looked at there. We just looked at the spectrum. So we know that it can be protonated and deprotonated. We know that's going to cause differences in its spectrum, what it looks like. And from that information, we can determine the pKa of the acidic groups there. Okay, and what we're actually looking at, if we go back here, is this group here, okay? So that phenolic group. Okay, so the information that you could be presented with in the question is the absorbance of a fixed concentration of phenylephrine at 292 nanometers is found to be 1.224 in 0.1 molar NaOH and 0.02 in 0.1 molar HCl. Its absorbance in buffer at pH 8.5 is found to be 0.349. You're being asked to calculate the pK value of that acidic phenolic hydroxyl group. First, let's look at what information is irrelevant and relevant. Again, this 292 nanometers is the wavelength at which the experiment was run. It is just information. It is not. It doesn't factor into the calculation. We have an absorbance value of 1.224. Okay, so that is the ionized species. Okay, so we have an ion. Okay, if we go back and have a look, when it was deprotonated, we had more ions up here. Okay. Okay. What else are we looking at? So 0.1 molar and 0.1 molar here are concentrations, and there's no need for them in the calculation. Again, this is just telling what procedure was run. So again, these are not going to factor into our calculation. 0.02 is our U, it is our unionized species. its absorbance and buffer at pH 8.5, we do need a pH value, okay? So this should be supplied to us. So our pH value here is 8.5. And then finally the absorbance, the measured absorbance, was found to be 0.349. So the main area that we can go wrong here is finding our unionized and our ionized species. So just be very, very conscious of that. We should always end up with a positive value here, okay? So just be mindful. So, and again, once we have that information, we are just subbing everything in, making sure that you do the calculation properly, as in do your log values first and do your BOMDAS, if you remember that first. So subtract 0.349 away from 1.224 first and divide that value by 0.349 minus this. So do it step by step. It's the best practice to be in. Once you've done that, then get the log value of the whole value and then add the two together. Another calculation that can be used is the pharmaceutical quantitative analysis, okay? So this is basically us trying to determine, trying to quantify, the amount of an active pharmaceutical ingredient in a tablet or in a sample. And this is largely based on using that standard absorbance value, that standard A1% value for those active ingredients being assayed. These methods also assume that you have perfect conditions, okay? So you have no interference from excipients, okay? So your preservatives, your colorants, your bulking agent, etc. are not absorbing in at that wavelength. And it's also assuming that you have a perfectly dissolved sample. So you have no suspended matter which would cause light scattering. So we're going to have a look at an example of one of these. They are far more detailed questions. There's loads of information. So again, it's very important for us to try and decipher what is relevant and what is irrelevant. And just, what steps are actually involved. So we'll look at this in more detail. So this is the type of question that you could be presented with. And as I said, there's lots of information in it, and typically the first lot of information is going to be based on the procedure. Okay, so how does compound or how does tablet was actually prepared in the lab? Okay, so you're being told that you have tablet powder containing about 0.25 grams of furosemide. It is shaken with 300 ml of sodium hydroxide, and we are extracting that acidic furosemide. You're making up the extract of 500 ml, and then you're doing a dilution. Okay, and this is probably the first piece of information I tell you to pay attention to. Within your procedure, you're more than likely always going to be going from your stock solution, your concentrated solution, to a diluted solution. And we want to take note of that dilution factor. So you're taking 5 ml of that concentrated solution and you're making up to 250 ml, which is a 50 times dilution. So that's the first little piece of information that I would jot down. You're then being told that you'd read the absorbance, because obviously you want to get an absorbance value for this. And then you're told that you have an A1% value at 580, and this may have been obtained through the British Pharmacopoeia. So two pieces of information that we have from our section on our procedure is our dilution factor, which we said is 50, and we've been told the A1% value, which is 580, and we would have gotten that, say, in the lab from our British Pharmacopoeia. You've also been given some other information that is very, very relevant to the calculation itself. So right now you're being asked to determine the percentage of stated content in a sample of furosemide. So the stated content should be 40 milligrams of furosemide per tablet. We are going to see what we get after going to the lab, running this experiment. Do we get 40 mg? So can we say, yes, we have 100% of stated content, or do we get more, or do we get less? For the experiment, we have a weight of the 20 tablets used, which is 1.656 grams. We have the weight of the tablet powder taken, which is 0.5195. And of course, at the end of the experiment, we would have ran this in a cuvette in a UV, and we would have gotten an absorbance value of 0.596. Loads of information there. Okay, so let's just have a look at the steps that are typically involved. So we have to first of all determine the content of furosemide in the sample used. So you were told that you weighed out 0.5195. We're going to divide that by the weight of the tablets, and we're going to multiply that by 40. Okay, multiply that by the stated value. Okay, and we get a value of 12.55 mg. And we're multiplying that by 20 because 20 tablets were used. Okay, so that is 251 milligrams. We're just going to park that value there for a moment. The next we'll consider dilution factor. Now we already did work this out. We said 5 mils to 250 mils, so just divide 5 into that and we'll say our dilution factor is 50. So we'll have to remember that for the end. We want to find out the concentration in our diluted tablet extract using our Beer-Lambert law. So we have an absorbance value and we have an A1% value. Okay, so we should know how to get a concentration using those two values, and we'll get them in grams per 100 mils. So we were told that in the lab at the end of the experiment the absorbance value was 0.596. We can divide that by our A1% value. So this is a calculation we did earlier on, and so we should be familiar with that. So based on that, we'd be told then that we'd have 0.001028 grams per 100 mils. We want to go from grams per 100 mils to milligrams per 100 mils because, again, we know that our answer should be in milligrams because we need to be able to compare it to this. So to go from grams per 100 mils to milligrams per 100 mils, we times 1000. And that will say that there's 1.028 milligrams per 100 mils. We now factor in our dilution factor. Okay, so we're going from our diluted sample to our stock sample essentially. Okay, so right now we have 51.40 milligrams per 100 mil. However, our extract, our original extract, was made up to 500 mils. So therefore, if we want to go from milligrams per 100 mil to milligrams per 500 mil, we multiply by 5. So that will tell us that there's 250 milligrams of furosemide in that original extract. So we come back up here and we would have found out, so within those 20 tablets, we would have had 251 milligrams. So now we divide our answer, okay, our experimental answer, by that expected answer times 100%, and we find out that we have 102.39% furosemide in those tablets. And typically what we'd also do is compare that to the British Pharmacopoeia or US Pharmacopoeia range or allowable range. So oftentimes they will say that you're allowed between 90 to 110% of the stated value, and if we were in the lab we'd say, okay, does this value fall within that stated allowable range? So there are a lot of steps in here, so just be wary of it. Again, I've given you more examples of these in that problem sheet for you to try yourself and see how you get on. Okay, they do all typically follow this layout. Okay, so first of all, determining the content of furosemide in the sample used, noting your dilution factor, using your absorbance value and your A1% value to determine the concentration in your dilute sample, factoring in any dilutions, keeping an eye out for how much it was made up to, and then doing your percentage. Those steps should be fairly consistent, okay? So just try and get your head around these two slides here. Okay, so we're moving on. We're looking at difference spectroscopy. So this is often used when we have more than one thing in a sample. So we just talked about our qualitative analysis there. It assumes perfect conditions, that we have nothing else in our sample to interfere. But that's not always the case, particularly when we're dealing with pharmaceutical preparations. We're going to have preservatives, we're going to have colorants, we're going to have coatings, we are going to have bulking agents and other excipients. Okay, so what we want to do is having the analyte of interest, finding something that makes it different to everything else that's in the sample, so we can run the UV in conditions that suit that sample only, and so we only get the UV. Okay, so let's look at an example here. So we have a preparation of aspirin tablets, and they contain a variety of different compounds. But let's say we only want to get the wavelength, or sorry, we only want to get the UV vis spectrum of aspirin, okay, not the other ingredients. So we kind of have to have a look at aspirin, look at its structure and say, what can we manipulate or what can we take advantage of on the structure of aspirin? What makes it unique? And when we look at that structure, aspirin is the only group that contains its chromophore, which is a carboxylic acid group, that's COOH group, and this can be manipulated through pH. We can protonate and deprotonate this, and that will change the spectrum. So that really, really useful for us. So we can take that, we can use that, okay? So if we deprotonate it, okay, so again, if we remove the hydrogen or that proton from the carboxylic acid group, that will change its, it will change its structure by making lone pairs of electrons available, and that will allow those lone pairs of electrons to interact with that benzene ring or original chromophore. That will also change the UV spectrum. So we'll have a new peak that will appear at a longer wavelength, and that will be solely due to the presence of those lone pairs of electrons. And that value can be used to determine the concentration of aspirin in that tablet. So that's really, really important to us. Okay, so we can see how being conscious of our structure of a compound of interest, and also knowing how to manipulate it, be it through pH or being aware of our oxychromes and how they can be manipulated through pH is very, very important to us. So that is different. So we can also have derivative spectroscopy. So with UV vis, if we can't find, like what we did with aspirin there, if we can't find something that makes it, makes that particular compound special or different, UV vis in general has a very low selectivity. So we can have very well-defined bands, but they might be distorted by the background, okay, everything else that's going on in there. When we have very simple samples, so let's say we have solvent plus sample of interest. We can typically just blank the instrument, okay, so we can just say this is a solvent to use, we don't want to pay attention to that, so ignore that and pay attention only to the sample. However, as we have samples that are more complex, that method is no longer effective. So we have to turn to another method called derivatization, and this is a simpler method or simple method to increase the selectivity, and it allows us to remove interferences from other compounds. So again, you don't need to start going down the road of lambdas and deltas and stuff. Just be aware of how it works. Okay, so we're basically taking our normal spectrum and you're just derivatizing it. Okay, so we can have several derivatives. So we can have D0, which is 0 order, we can have first order, second order, and so on. It can go all the way up to fourth order. So just be aware, the more we derivatize it, the more likely we are to get background noise. So if you, the rule of thumb is if you achieve a good result at a lower order, there's no point going to any of those higher orders because we're just wasting time and effort. And when we're talking about derivatizing, this is what we're talking about. Okay, so we have our standard peak here that we'd have, okay, our 0 order, and then we can start to derivatize it. So we can have our first derivative here, we can have our second derivative, our third derivative, and our fourth derivative, and so on. Okay, you don't need to know this part, you just need to be aware that we can derivatize it. It does improve selectivity of more complex samples. And again, we will be looking at this this week. Actually, we'll be looking at it when we take ephedrine and we use second derivative spectroscopy to look at ephedrine only and disregard the other components of a cough syrup. So the most common method of recording your derivative spectra is the use of a dual wavelength instrument with 2 monochromators operating at the same speed. We have a lag of a few nanometers between the two. So basically what will happen is, okay, so mathematically you're taking the difference there, divided by a constant wavelength lag, and you're plotting that against the average length. Again, I don't expect you to know this in detail, I just need you to know that's going on, that's what it is happening. So our advantages: we have better resolution of overlapping bands than if we had a 0 order, okay, or fundamental spectroscopy, and it allows us to get a more accurate determination of the lambda max of an individual band, okay, and the individual band is relating to one very specific analyte. It's primarily being used in pharmaceutical analysis of assaying main ingredients in the presence of other components and excipients. So again, that's why we need it, because we don't have a simple sample anymore, we have a complex sample. We can also use it to look at 2 or more compounds. And then finally, we can obtain spectra in solutions with high scattering, which rarely is possible, okay, but we can do that using the dual wavelength instruments. So again, just to be aware of why we're using it. Finally, we're coming down just UV vis overall, how does it use, and we're going to look at its advantages and its limitations. So the last few slides. The simplest application of UV vis is just to quantify how much of a substance is in there. Okay, again, we can do that in moles per litre or grams per 100 mils. We can quantify the drugs and formulations when there's no interference from the excipients. We can determine our pKa value, so the strength of the acid in some of those drugs. We can determine partition coefficients and solubilities of drugs. We can determine the drug release profile of a formulation with time. We can monitor reaction kinetics, and then we can also use the UV spectrum as an identity check in a we can use the UV spectrum of a drug as an identity check. So we can look at some of the applications in a bit more detail. So let's look at the partition coefficient. So the partition coefficient of a drug between water and organic solvent, so again, how soluble is it in water and the drug, can be made by shaking the organic solvent and water layer together and determining the amount of drug present in each of them. If we use buffers or different pH values, the variation of partition coefficient with pH can also be determined. Okay, and this can also provide a means of determining pKa value. Solubility, okay, so again, how soluble is a drug in a solvent? So we could be using water, we could also be using alcohols, DMSO, and so on. So you're taking the drug, you're shaking an excess of the drug in water, or buffer, or whatever you're using, until the equilibrium is reached. Okay, so how much we can actually get in there until it's a saturated solution, and then you're using your UV vis to determine the concentration of that drug based on the absorbance value obtained. We can also look at drug release. So UV spectrophotometry is routinely used to monitor the in vitro release of active ingredients. So again, for simple formulations, you just look at its lambda max. If we have excipients that also can absorb in that UV region, we might need to pay a bit more attention, and we can also use HPLC coupled to UV detection too. On our final slide, there's obviously strengths and limitations, just as there are with any spectrophotometric method. The strengths are it's a very easy to use instrument, they're more often cheaper than other instruments, they're quite robust, and we do get good precision from them. They're very routine, okay, so we can look for physical-chemical properties, which we need to be known for formulational purposes, and then some problems can be overcome, so again, by using difference spectroscopy or using derivative spectrum. However, there will always be limitations, so it is only moderately selective. So we've already said that with our derivatives. We can only go up to a fourth derivative. We also risk increasing noise there. If we look at our difference spectroscopy, if we had another drug that had a carboxylic acid group on, then our difference spectroscopy would be no use to us. So this is very heavily dependent on the chromophore in question. For example, we can also look at a colour drug. So when that has an extended chromophore, that is obviously far more distinctive than a drug with a simple benzene ring. So it really does boil down to the chemical structure there. And these methods are not readily suited to analyse a mixture. Okay, so again, we do need to put a bit more work in there, and it won't always be applicable.